All right, today we're tackling a really wild idea. What if the bizarre rules of quantum mechanics aren't the fundamental bedrock of the universe? What if, instead, they're actually created by the very act of us looking at it? We usually think of physics as describing a world that exists out there, totally separate from us. But what if that's not quite right? What if the reality we see, the reality we measure, is something else entirely? And that leads us to this pretty radical alternative we're going to explore. The idea that the quantum world is kind of like a user interface, a reality that's constructed for an observer by an observer. So, how on earth would you even begin to build a universe that works like that? Well, it turns out you might only need two surprisingly simple ideas. To build this whole new way of looking at things, we only need two core ingredients. And forget about particles and forces for a minute. The foundation here is way, way simpler. Let's break it down. So, our first ingredient, it's not a particle, it's not a field, it's a network of conscious agents. Now, agent sounds kind of fancy, but really it just means anything that can have an experience. Could be a person, an animal, maybe even a simple camera. The important part is that we can draw a map where every dot is a possible experience for that agent, and the lines between them show the odds of jumping from one experience to the next. And the second piece of the puzzle completely rethinks what observation even means. It's called the trace. This isn't just a passive glance at the world, it's an active process. When an observer looks, they are essentially tracing a path through that huge complex map. And by doing so, they create a smaller, more focused map of what they actually experience. Okay, so with just those two things, a network of experiences and this idea of tracing a path, we can actually start to build the familiar features of quantum mechanics. So first up, let's see how something as basic as a wave can just pop into existence. To get your head around this, just picture a circle of bells. If you go around and strike every second bell or every third bell, you create this repeating pattern, right? A stable cycle. Well, that repeating pattern, that mode, is exactly what we're talking about. And this is where it gets really wild. These stable, repeating patterns inside our network of experiences, they have all the same mathematical properties as waves. We didn't have to add waves into our model. They just emerged, all on their own from these really simple cyclical rules. Okay, so we've got waves, pretty cool. But what about particles? Well, let's see what happens when we just add a second, identical conscious agent into the mix. The best way to think about this is with two dancers doing the exact same routine. There are really only two fundamental ways they can relate to each other. They can move together in perfect sync, that's in phase, or they can move in perfect opposition, that's out of phase, that's it. And that simple symmetry literally splits their world in two. The in-phase or symmetric movements behave exactly like one family of fundamental particles, the bosons. And the out-of-phase or anti-symmetric movements behave just like the other family, the fermions. I mean, just stop and think about what this means for a second. The two huge classes of particles that make up our universe might not be some fundamental given. They might just be a direct mathematical consequence of having two identical observers in a system. The system just naturally splits into two styles, and there's no way to cross from one to the other. All right, next up, the big one. We're going to tackle one of the weirdest, most famous effects in all of physics, quantum interference. You know, the whole mystery at the heart of the double slit experiment. But instead of thinking about mysterious waves canceling each other out, let's try a different picture. Imagine you have two separate road systems. The traffic in each is totally predictable, but what happens when you build a bridge connecting them? All of a sudden, you've got new intersections, new roundabouts, new ways for traffic to flow that were completely impossible before. And believe it or not, that's exactly what's going on in our agent network model. You have path A, and you have path B. Separately, their outcomes are simple. But when you join them, when you allow an agent to potentially experience either one, you create new loops and new pathways in the math that didn't exist in either part all by itself. So what's the big takeaway here? It's that the outcome of the combined system is not just the sum of its parts. Those new connections fundamentally change the probabilities. That right there is quantum interference, but it's explained by the shape of the map, not by weird, ghostly waves. So let's pull all these threads together. We've got waves coming from cycles, particles from symmetry, and interference from new pathways. Turns out, there's a way to see all of this as one single, beautiful geometric object.
A great way to wrap your head around this is to think of a theater with these modular sets. Our observation, our trace, is what chooses which set the play gets performed on. And when we combine systems, like opening both slits in the experiment, it's like building a bridge between two sets, allowing for brand new scenes that couldn't have happened on either set alone.
And this big geometric map of possibilities, it actually has a name, the markovian. It's a structure where each face represents a different potential reality, a different channel. The act of joining networks lets us jump to new faces on this map, unlocking outcomes that were totally inaccessible before. It's literally a map of reality, and it's shaped by observation. So let's do a quick recap. Starting with just a network of observers and their experiences, we've seen how all these core quantum features just pop out. Waves? They emerge from stable patterns. The two types of particles, bosons and fermions, they emerge from simple symmetry. Interference? That comes from the new paths created when we join networks together. Even other weird rules, like the fact you can't perfectly copy a quantum state, the no-cloning theorem, they also fall out naturally from the math of this model. And this brings us to one final and kind of profound thought. If the very structure of our physical world, the waves, the particles, all those bizarre quantum rules is an interface that's constructed by and for observers, well, what does that imply about the nature of the observer, about us? It suggests we might not just be passive witnesses to the universe, but in a very, very real sense, we might just be its co-creators.